So, sorry about that. I had to restart. And so our intro got a little bit cut off here. I just need to make sure that the mic is working. Okay, good. Remember that we are live on the Piazza Q&A. And of course, we're live, we have the chat going on over here in YouTube. One thing, unfortunately, today is it looks like CS50 is down, at least for me. So we're going to be doing everything in Java instead. Okay. All these every demonstration that I'm going to do today is basically the same in both languages, as far as sorting is concerned. Right? Hopefully it'll get fixed by the time we're done here, and we can check out how to do this in C. But basically, where we left off last time is that we looked at linear searching, and then we found a better algorithm called binary search that was exponentially faster. But the thing is, it requires it to be sorted. So that's our next topic. How do you sort a collection of things? Now, this could be an array of integers, it could be an array of doubles, it could be an array of strings, it could be an array of films, right? It could even be, a list of those things. And how do you end up sorting it, right? There's a huge variety of different approaches that you can sort by a film. You can sort it by the title or by the director, last name, first name, or you can sort it by the Internet Movie Database rating, etc., right? So hopefully it's fixed now, right? Let me know if you can't see the stream. I'll go ahead and still. All right. But otherwise, it's showing up for me. Okay. So hopefully that has been resolved. I don't know if it's a general internet issue today or what, but CS50 is also down. Again, so there's a huge variety of algorithms with different algorithmic properties and different strategies, and usually, there are a few core sorting algorithms that are used that are fast, but there are some instances in which you may want to use a slower sorting algorithm because it has different properties. Like, for example, I know that there's Garmin comes in a lot and to try to recruit students. And they gave a presentation one time where they basically chose to use bubble sort to sort a list of airports on their embedded systems. Even though it was slower, it was less memory intensive. And on their embedded system, that was what was important. So there might be very good engineering reasons to do so, to use a slower sorting algorithm, but those are separate concerns, separate engineering concerns, basically. There are at least a dozen different algorithms that we could cover. I don't want this to turn into a sorting algorithm course, but of course, it's sorting algorithms. It's a concept that's easy to get, and so you'll see that there's a lot of videos out there on this sort and that sort and this sort, and this is how this one works. It does present an opportunity to learn about different algorithmic strategies like divide and conquer or decrease and conquer, stuff like that. But we're going to go ahead and keep it simple, and we're going to go ahead and look at two sample sorting algorithms. The first one is called selection sort. And it's pretty straightforward. In fact, if you had an arrangement of stuff on your desk, how would you go about arranging it? So you want to sort it. You go through and you take, okay, this is the smallest one, I'll put it over here. Now what comes next? Oh, this one, and I'll put it over here. This is the smallest one, and and then you've got it arranged after a while. And that's what selection sort does, basically. The basic idea is that it iterates through the array and finds the minimum element, or more accurately, the minimal element, because there of course could be duplicates. There could be two ones in there, right? Finds the minimal element or a minimal element, even better, right? And then it swaps it with the first element, right? Then it repeats. Right? So how does it repeat? It iterates through the remaining elements and finds the next minimal, right? The second smallest right? And this is assuming that we're sorting in ascending order, of course. That's the natural ordering. Of course, you could have a sorting algorithm where I don't want that. I want a descending order because I want Zermello up here and Anderson down here if you're sorting by names or something, right? So you're iterating through the remaining elements and finding the next minimal, the second smallest, and then you're swapping it with the second element, right? So you're repeating this over and over again. That's the first iteration, that's the second iteration. How do we go about thinking about this in more general terms, in abstract terms, on the ith iteration? On the ith iteration, then the first I minus 1 items have already been sorted. So among items I through n minus 1, assuming that we've got 0 indexing, of course, we find the minimum and swap it with the ith element. This is how you take a basic idea and you generalize it. You make it more abstract by looking at, okay, that's the first time, that's the second time, that's the third time. Is there a pattern there that I can follow? Oh yeah, on the ith time, what I was doing is I was finding the ith smallest one and I was putting it at the ith location. Right? And that gives you an idea of how you can then generalize that. How many times do we repeat this idea? We repeat this until all items have been sorted, right? And when have all items have been sorted? So if I've got n items here, I've sorted the first n minus 1 of them. The n minus 1, or the last one at the nth one, it's already where it needs to be, right? So you sort this for n minus 1 iterations, right? And you don't have to do that last iteration because all this stuff has been sorted already. You're looking at this element right here. Oh, I need to put it where it needs to be. So among this element right here, I'm going to go ahead and find the minimum. Well, it's only one element, so it's already minimum. And okay, I'll go ahead and swap it with itself. And you end up doing nothing. So that's why we can stop short there. Hopefully this does work. Let me go ahead and grab this array right here. We're going to be working with this one. I just randomly wrote stuff down. Escape this. Let's go ahead and look at selection sort here. And I will create an array, not this random array, but this array. And I will sort it. Right. Here's the idea, right, in action. And let me go ahead and pause and get rid of this, get rid of this. So we started out here at 2. This is the ith iteration. This is the first iteration. Right? We're going to go through all the elements and find the minimum. The minimum here is 1. Right now, this 2 has been the minimum. 7 is not minimum. 5 is not less. 4 is not less. And I will go step by step. 3 is not less. 6 is not less. Oh, 1, that's less. That's a new minimum. Okay. So then compare 8, compare 5. Okay, we found that 1 is the minimum, and so we need to put it where it needs to be by swapping it with 2. Okay? Now, on the next iteration, 1 is where it needs to be. We leave it alone. We only look at the remaining elements. Right? 7, okay, well, that's the minimum so far. Oh, 5, we found something that's even less. 4, we found something that's even less. Even less. 6 is not less than 3. 2, oh, that's even less. But of course, we still have to compare the rest of them, finding that 2 is the minimum, and we end up swapping with 7. Right? Next iteration, this first 2 have been sorted, and we look at the remaining elements. Right? 5 is the minimum. Okay, 4 is even less, so that becomes our minimum. 3 is even less, so that becomes our minimum. And of course, we make a comparison with the rest of this stuff, finding that 3 is in fact the minimum and swapping it. And then it continues. Right? So, play. Right? You can see this play out here with the rest of them. Okay? That 5 then gets put where it belongs. On the next iteration, the second 5 gets put where it belongs. And then the remaining stuff is not necessarily yet sorted because we threw 6 over to the side there. 8 and 7, there we go. Hey, great. And now it's sorted. Right? Okay, that's the idea. Let's actually program this now. Oops. Stop. What's going on? All right. Sorry, go ahead.
That seems kind of slow.
It does seem kind of slow. In fact, what were we doing all the time? We were starting over here, walking all the way over here, starting the second one, walking all over here, starting at the third one, walking all over. Remember the painter from Tuesday? The painter that dipped his paintbrush and then walked down to where he was painting and painted, walked all the way back, dipped again, walked all the way back and forth. That's exactly what this is doing, and it's going to be inefficient. How inefficient, though? Let's go ahead and understand this, though, by programming it first. And so again, CS50 is acting up, so I'm going to go ahead and do this in Java instead. Normally, if I were doing this in pure Java, of course I would use a list. But I want to demonstrate this for just a regular old array. Public static void selection sort. And what we're going to take is an integer array. Right? We don't need to pass in the size here like we do in C. Why? Because array.length gives us the size of the array. All right, so here's the idea. So what I'm going to do is I'm going to go over each one of those iterations. How many times are we going to do that? Well, we're going to do it for the first one, then the second one, then the third one. This is why we call it selection sort. On the first iteration, I'm selecting the first element. On the second iteration, I'm selecting and placing the second element, etc. Right? So I will iterate over, to place the ith element. So I'm going to have a for loop. For int I equals 0, I is less than something, I plus plus. And what I'm going to do is I'm going to find the minimum among elements I through n minus 1. Right? Again, remember, think in abstract terms. Jump into the middle of the algorithm. Right? This part has already been sorted over here. Here's the ith element through the n minus 1th element. That's what I need to sort. So I don't touch this stuff over here. I need to start at the ith element and look for the minimum among the rest of it. That's another loop. Right? So for int j equals, I start at I, not 0. J is less than n, j plus plus. Right? If the jth element is less than the min so far, update the min. So what we need to do is keep track of the minimum, and I'm going to do that by keeping track of the minimum index. Int min index is equal to, we'll start at I, right? And then I will compare the min index that I found so far, compare it to the jth one, the jth one, jth one. Oh, sometimes I might end up updating this, and this is the new minimum, right? So I'm going to update the min index if that is in fact true. So if array sub j is less than the array sub min index, right? I'm keeping track of the index here because I don't want to just keep track of the value. I want to know where it is so that I can swap it with the ith element, right? So min index is equal to j.
Technically, that's all that matters.
Yep, that's all that matters. And keeping track of the index actually gives you more information. Because given the index, you can always look up the value, like I'm doing right here. But just keeping track of the value, I can't, where was that again, right? And after this loop, after I've got the minimum index here, I'm going to swap the ith element and the min index element, right? Okay. All I need to do that is a temporary integer to take the array's ith element, store it. Into the array's ith element, I will place the array's min indexed element. And then finally, the min indexed element takes on the value of temp. Right? Just a simple swap. Okay? Now I'm going to back up here because we've got two issues. One of them is, do I really need to start my loop at I? Remember, I'm looking at I through n minus 1. Right? If I start here and assume that this is my minimum, do I need to compare it to itself? No. So I will go ahead and increase, or start at I plus 1 instead. The second thing I need to take care of here is, where do you stop?
I minus 1.
N minus 1. Why n minus 1? Good. You don't need to check the last. Once you've sorted the first n minus 1 of them, you don't need to put that guy is already where he needs to be. Right? So you don't have to do that. Now, of course, we don't have n here. We have array.length. All right, there we go. And of course, down here, array.length. Yeah, go ahead.
No, yeah, good job.
Okay. So let's go ahead and selection sort array. And I don't need this n anymore, but that's an artifact of me copy pasting from C. All right. Thank you all. It is running. Thank you. Let's go ahead and play this. Is it showing? Yeah, it's showing. All right, so 1, 2, 3, 4, 5, 5, 6, 7, 8, right? Excellent. It has been sorted. Okay. So there is selection sort. Now, remember, when we looked at linear search versus binary search, we wanted to capture a notion of work, of how good or how bad is this algorithm, right? So let's look at analysis. Right? How many comparisons, or you know, first of all, what work does this algorithm make? Right? And hint, since I already gave it away, comparisons, right? But there's also another answer here, right? So remember that, yeah, there's an initialization here. There's a variable being updated. You're doing a comparison here. You're doing an addition, right? Yeah, fine. You're also doing that over here, but those are necessary for the control structure of the algorithm. We don't want to pay attention to those. This is only a one-off, right? It's only done once for each one of these loops. What we want to do is we want to look for the most common or the most expensive operation. The most common operation is probably going to lie inside, because we've got a for loop and a nested for loop here. The most common operation is going to lie inside those two loops. So what is happening here with this if statement? Well, we've got an assignment, but that's not always executed. It's only executed if this the comparison is true. But we always make the comparison. So that's a good candidate right there, the comparison on line 21 of this code. But you could also say that, well, we're also doing swaps. Maybe swaps are expensive. And if you've got an engineering problem where, in this particular application, we want to minimize the number of swaps. It can run slow, that's fine. But we want to minimize the number of swaps because it's memory intensive. Cache misses are more expensive than just doing more comparisons. Fine. Then that's another alternative. Algorithm analysis, it's choosing what's called your elementary operation is an art. It depends on what you are analyzing it for. And it can lead to different answers. It can lead to different analysis that this is actually quite efficient as far as memory usage is concerned. It's inefficient as far as computation time, right? Whereas this one over here is more efficient in computation time, but less efficient on memory, right? Those are practical engineering questions that you should be asking. We're just going to keep it simple, though, and we're going to go ahead and go with comparisons. Yeah, go ahead.
So memory doesn't exactly equal computation time?
Not necessarily. Memory is not necessarily equivalent to computation time. There might be a trade-off because, I mean, as you go down in the memory hierarchy, it gets larger and cheaper, but it also gets way slower, right? Memory on the chip itself, if you can keep stuff on the chip, that's going to be fast. RAM is a little bit slower, but it's nowhere near as slow as, say, even SSD memory, and then SSD memory is faster than hard drive because it's mechanical. But each one of those is cheaper, and larger, therefore larger, but also slower. So because the memory data has to travel up and down this hierarchy depending on cache hits and cache misses and stuff, right? So that's why you know it's better to have a larger cache on your processor because then you can have a really fast processor, but if you have a garbage cache or a small cache, then that's your bottleneck. That's where you're going to be spending all the time loading up that memory, right? All right. So what work does this algorithm make? Comparisons. All right. How many comparisons are made to sort an array of n elements? Right. Okay. Well, we're not going to go through a full formal analysis here. Otherwise, I'd have to pull out a pen and paper and start doing some sums. But we can go ahead and get an estimate. Right? So let's take there's one comparison made on this line right here. So now the question becomes, how many times is this line, or this block of code more accurately, how many times is this block of code executed with respect to the input size? Well, sometimes it executes very, very little. Sometimes it executes a lot. For example, on that first iteration, we had to compare that element to every element after it. Right? So there were n minus 1 comparisons. On the second iteration, we didn't have to compare it to the first element anymore because it was over here. So there was n minus 2 comparisons. Right? Down to the last iteration. The last iteration, we only had one element, and we only had to compare it to another element to see if we should swap those. Right? So it's kind of like linear search. Sometimes you can get lucky, sometimes you don't get lucky. So what I'm going to do is I'm going to go ahead and overestimate here. And what's the maximum number of times this line is executed? On the first iteration, we said that there were n minus 1 times. Right? So 1 comparison times n minus 1 iterations on the first iteration. So that gives us an overestimate. Okay? Now, this block is executed for each iteration of this outer for loop. How many times is this outer for loop executed? For 0, 1, 2, 3, all the way up to, but not including n minus 2, or n minus 1. So, in other words, n minus 2. But we start at 0, so it's actually n minus 1. n minus 1 times, what do we get? n minus 1 squared times. I don't like that not 1. Let's go ahead and simplify it even further. Again, this is a kind of an overestimate, so we'll go ahead and do it a little bit of a more of an overestimate, because n is larger than n minus 1. It makes about n squared, oops, sorry, there, LaTeX, right? N squared comparisons, right? Now, again, the full analysis would have me setting up a summation, setting up an inner summation, and summing those up. Don't worry about that, okay? In other words, selection sort is a quadratic sorting algorithm. Remember linear search? Why do we call it linear search? Because it made a linear number of comparisons for an array of input size n. Binary search was a logarithmic algorithm because it makes log n comparisons based on n being the input size. This one is called a quadratic sorting algorithm because it makes a quadratic number of comparisons to actually sort it. Right? How bad is that? Right? How bad is this? Right? Yeah, it is pretty bad. How though? Right? Suppose you want to sort an array of 1 trillion elements. That's 10 to the, how big is that? 10 to the what? So 6 billion, that's million, billion, trillion would be 12. There we go. Good. So it would end up making how many comparisons? Well, that figure squared. Do you have a name for that? Do you know what that is? Equals, yeah, it's 10 to the 24th, right? That's 1 septillion, I think, right? Let's find out. So I've got Wolfram Alpha up here, 10 to the 24th. Yep, 1 septillion operations, right? Comparisons. Operations, all right. Now, before you think, oh, that's no, who would want to sort an array of 1 trillion elements? That's too big of data.
Would that be enough to justify making that function in the first place?
You've got 1 trillion elements. Is that really big data? Think about how, if it was integers, then there are 4 bytes per element, so that's 4 trillion bytes, so that's 4 terabytes. Right? That's a typical hard drive nowadays. Right? I've got a 1 terabyte SSD just as a backup in my backpack. I think that this, my Mac here has 2 terabyte hard drive, and of course external hard drives for large scale storage, 8, 10, 15, 16 terabytes. Who knows what they're gonna have it for Black Friday sales now, right? But it's not that big of a data, right? So, I mean, it's large, but it's not big data as in like the Large Hadron Collider data that they get over at HCC, the Holland Computing Center. The Holland Computing Center is is a tier 1 or a tier 2 data processing center for the Large Hadron Collider. They get that kind of data every second, right? Or every few minutes or something like that. So that's not big data. How long would it take us to do this if we could perform billions or trillions of operations per second? Right? So one way of measuring the speed of a computer, a processor, or say, I looked this up right before class, is the 1080, 1060 can achieve roughly almost 7 teraflops, right? 7 T-flops. T, tera, that's trillion, so 7 times 10 to the 12, right? Teraflops. Tera being trillion, and flops are being floating point operations per second. Now, that's not an exact comparison. In fact, the article that I was getting this from was actually an article pointing out that flops are no longer a real measure of speed. Because if you just go by flops, then they said that the 390 series actually achieved 136 teraflops or something like that, but based on just the formulas for comparison. And of course, it was not 20 times faster. It was only 140% faster or something like that. So it's not an exact comparison, but it's a ballpark figure here, right? That's the number of seconds that it would take. Yeah, in fact, 1 trillion seconds, right? 1 trillion seconds divided by 7, whatever that happens to be. Well, okay, that's seconds, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. That gives us days. That's 1,000,000 days, right? So let's go ahead and convert that to years, 365.25 days in a year. That's 4,500 years to compute this data, right? So at 7 teraflops, roughly, that would take 4,500 plus years to compute, right, to actually sort. That's terrible, right? That is not at all practical. Again, this is not big data, right? Even if I kick that down a notch, and said that, oh, it's not 1 teraflop of data, it's going to be, or not 1 trillion elements, just say 1 billion elements, right? Or maybe even just 1 million elements. 10 to the 6th squared would be 12. Okay, now we're going to get down to fractions of a year. But if so I'll say that it was 1 billion. 1 billion elements squared gives me 10 to the 18. Okay, so it's a fraction of a year, but when you convert that to minutes, that's going to take maybe an hour, right? In fact, let's do that. We know that this is the number of hours that it would take to sort, 39 hours. So it'd take,
It's like almost 2 days.
yeah, almost 2 days there to sort. Right?
It's not,
That is not at all practical. Here's another way of looking at it. Suppose you look at it from the following. Suppose you want to double the input size, right? You go from n to 2n, right? How many more comparisons will you need to make? Right? Well, if I go from n to 2n, since it's squared, right, that's going to be 2n squared, which is equal to 4n squared. 4n squared, there we go. In other words, 4 times as many operations, or 4 times slower, right, as a consequence of that. So it's not good. Can we do better? And the answer is yes. We can go quicker. Quicksort, okay? So I'm not going to present the full code here, but here's the basic idea. Right? We're going to select a pivot element. It's usually the first one. And this pivot element, what we're going to do is we're going to look at all the other elements. Anything that is less than this pivot element, we're going to put it over here. Anything that is greater than this pivot element, we're going to leave it over here. Right? And then we're going to put the pivot element right between these two things. Right? Sound familiar? That's from binary search, right? You look at the center one, and everything over here is less, everything goes over here is greater because it's already sorted. Right? And you can exploit that structure. We're going to exploit that structure by using recursion. Right? We then partition all elements to the left for lesser, right, or right, greater, and place the pivot in between them.
Should we try to put that in a while loop so that
Ultimately, when you program something like this, you would not use recursion. You would simulate the recursion using some sort of a while loop, yes, or an in-memory stack, even better, right? But the idea is that once we put everything less over here, everything greater over here, the pivot is where it needs to be. So recurse on this partition, recurse on this partition. We recursively sort the left partition and the right partition. Right? So again, let's take a look at a visualization of this. I'm going to grab my original array here in its order. There we go. And let's sort it. Go. Pause. Okay. All right. So our pivot element choice here is 2. Right? We're going to actually get kind of unlucky here because if I look ahead, 1 will go on to the other side, but all the remaining elements here are greater than 2, and so will remain over there. Right? So let's go ahead and continue this. That's on the right. Each one of those was on the correct side. Correct side, correct side, correct side, until it found something that was on the wrong side, and it swapped them around. Right? It continues. Correct side, and the two, which was our pivot element, is now placed between them. Right? We'll continue by selecting a pivot element. The left-hand side here, that's already sorted because by definition, one element is sorted. That's where the recursion stops. Otherwise, we're going to look at this partition, 5 through this other 5 over here, right? And we're going to, we've chosen this 5 as our pivot element, so 4 and 3 are going to go onto the other side. It's on the correct side, it's on the correct side, we don't do anything with it, right? 6 is on the wrong side, basically. It needs to go over here and make room for the pivot. So we find something else that's on the wrong side, and this one does not end up swapping them because it's equal, and so we end up just putting 5 where it needs to be. Right? 3 is sorted. 3 and 4 end up being sorted, but that's a different recursion. We recurse, and we find that those 2 were already in the place where they needed to be, and we continue with the rest. 6 is our pivot element. Anything that is greater stays on that side. Anything that is less goes onto the left side, and we end up swapping those and moving over the pivot element, and then it completes. Right? Turns out to be much quicker. Oh, see this code? Yeah. Or I don't know that they've published the code for this visualization here, but maybe.
Oh no, I mean like the code behind it. Like, are you gonna put?
Maybe if you look at the book, there's code in the book. Yeah, in the book I put full code. Now I don't do it like this. In the book I do it a little bit differently. I actually start at either end, I and J, and what my pivot element is over here. And what I do is I move I over until I find something that's on the wrong side, that is greater than the pivot that needs to go over there. I move this one in until I find something that's on the wrong side because it is less than the pivot element and it needs to go over there. And what do I do with them? I swap. And then I continue. until these two have met in the middle and you know that it's been partitioned. And that's where the pivot element goes. Right? So I do it a little bit differently in the book than this, but there are plenty of other alternatives. They're all inline quicksort. Okay? But that's the basic idea. Okay? So for code and pseudocode, see the book. What about our analysis here? Okay, so this one is a little bit more involved. All right, you can, in the worst case, or in the worst case, I'll say, not you can, but in the worst case, quicksort can devolve into selection sort. Right? How? Your pivot element ends up being the minimum, and then you put everything over onto this side and nothing over here. Right? In other words, what did you just do? You just put the minimum where it needed to be. Now the rest of this stuff, you select the maximum or the minimum as your pivot element. You end up putting everything, the pivot element over here, everything else stays in place, or the minimum and you put it over here, and again, you've partitioned it into an array of one less and an array of nothing. Right? So that's where the worst case comes in, and it devolves into a quadratic sorting algorithm. But in the average and best case, quicksort makes only n log base 2 of n comparisons or operations. Now, how do we get this? What you need to do is you need to set up a recurrence relation, a non-linear, non-homogeneous recurrence relation, and then you bring in this thing called the master theorem, which is just a plug and chug kind of thing where, okay, I've identified A, B, and C, and then I put it into the formula, and then it spits out a characterization of the algorithm. Don't worry about it. We'll cover that next semester. Okay? But otherwise, just trust me for now that this is n log base 2 of n. Why log base 2? Because we're splitting it in half each time, right? Roughly. Ideally, we're splitting it in half. And so we're getting the same performance as, say, binary search, except that there's that n term out front. This is known as quasi-linear, right? Quasi-linear sorting algorithm as a quasi-linear sorting algorithm. Why quasi-linear? It's kind of linear, right? It's almost linear. Quasi, meaning almost or half, right? Quasimodo, right? Almost man. Quasi-linear is almost, or quasar is almost a pulsar. Is that where they get that? I don't know. But anyway, it's almost linear because it's linear, but you've got this logarithmic term sitting there. Logs grow very, very slowly, as we've already seen, right? Let's just go ahead and map these two, right? These two algorithms. Let's go ahead and plot n squared and n log n, log base 2 of n. It doesn't matter what the base is. All bases are the same to within a constant using the change of base formula. Right? There we go. No. F of n is equal to, and then g of n is equal to. Hopefully that will log, there we go. No. That's not what I want. Yeah, this should, okay, fine. I'll be very specific. What? What is RE? You can't plot? You can't plot those two things? G of n. N is equal to 0 up to, say, 1 million. It's still not right. I mean, it's not treating that. That's treating n. I don't know why it's having such a tough time actually plotting. It was plotting this yesterday just fine. But in any case, what it should look like is, here's that n squared. Of course, it's a steep slope up here. I mean, it should look like this, right? Maybe it wants x, but it was working yesterday. All right, so that looks like a quadratic function, right? And let's go ahead and now plot g of n is equal to n. That's going to be a linear function. There we go. Now, can I extend that to times? I'll just go with natural log of n.
You can just imagine that this log base.
Okay, there we go. That's what I want, right? All right, so you can see that on the scale of 1 million here, obviously n squared is way up here. But this essentially looks flat, n log n, right? There is a huge difference between these two, the performance of these two algorithms. That's why we call it quicksort. It's much quicker. And in fact, it's much more practical, right? So again, let's take our scenario from before. Suppose you want to sort 1 trillion elements, right? It would only take, let me cut and paste this. It would only take n being 10 to the 12 log base 2 of n to the 12. Now, comparisons. Now, whatever that is, right? What happens to that 12? You remember your log identities? What happens to that 12, the exponent 12? It just comes out front, and you're left with log base 2 of 10, right? So what does that come out to? 10 to the 12 times log base 2 of 10 to the 12. We'll let Wolfram Alpha do our work for us here. There we go. And that turns out to be, well, that number. There's an approximation of it. But let's go through the same idea of that you have a 7 teraflop computer, or 7 teraflop computer, right? That's 7 times 10 to the 12 operations, floating point operations per second, right? How many seconds is that? 1/7 of that, so it's only going to be less than 6 seconds now, right? So 4,500 years versus it only takes 6 seconds to sort using a 7 teraflop computer.
Wow.
Astronomical difference, right? Now, these are both polynomial, right? I mean, n squared, that's a polynomial. N log n, that's quasi-linear. It's basically, it's larger than linear, but it's certainly way less than quadratic. So even from a practical perspective, there's no contest. Do not use selection sort. You would use quicksort. And in fact, the next thing that we're going to look at is you don't use either, right? You don't write your own sorting algorithms. Instead, you use what's already in the what's already in your library or your framework or your language, right? So we have a name for that. It's calling rolling your own. In practice, you don't roll your own. You shouldn't have to write your own implementations unless there is a very good reason to do so, VGR, right? A very good reason to do so. Like that Garmin fellow that wanted to use, or that needed to use a bubble sort because he had different engineering concerns. He needed to make sure that there wasn't too many memory swaps. And bubble sort did that for him, or whatever he was trying to achieve, right? For some reason, he used bubble sort instead of quicksort, right? You should look up AMD's graphic card. Actually, I did. In the same article, I think the 970 was like a few teraflops or something like that, right? I don't know, though. But certainly a month or two ago, I would have said AMD is definitely worth the price. But now with the 380s being like $500, you might as well go with those, right? So in practice, you use the built-in searching and sorting algorithm implementations provided by the language or standard library, right? To avoid, in fact, to avoid multiple implementations, most will use some sort of generic programming. Generic programming is where you don't have any regard for the type of thing that you are searching or sorting, right? The algorithm should be completely ignorant of that. The algorithm should just say, okay, these two things are out of order, I need to swap them. Or going through and finding the minimum, okay, this one is less than this one, so this one's the minimum. Or these two things are out of order, or these two things are in order, so leave them alone, right? Or these two things are equal, so it doesn't matter, leave them alone, right? All it needs is a way of determining what is the relative order of these two things. Do I need to swap them? Otherwise, the algorithm knows what to do, right? It knows how to sort. Yeah, go ahead.
Will you show, like, in this lecture, like, the standard libraries and stuff?
Absolutely. That's where we're going to get to next year. As far as C goes, though, say what?
Next year.
No. Well, today, right? Right. Yeah. If we can get to it, yeah. Let's see if I can bring up CS50. I'll let that load in the background. Hey, there we go. Finally. Okay. All right. So, go back to here. It might not load. Dang it. It looks like it's loading now, right? But first of all, we need to understand how this happens, right? General sorting algorithms know how to sort, right? But they don't know how to order, right? Sorting and ordering, colloquially, they mean the same thing. They're synonyms. But in the context of computer science, in the context of what we're talking about right now, sorting is arranging a collection of elements. Ordering is simply ordering two elements, A and B. Right? And we have something for that in both languages. In fact, every language is going to support something like this. In C, they're called comparators, right? In C. So in C, a comparator function is used to order elements. Now remember, ordering is just two elements, A and B. Are they in order, are they out of order, or are they equal, right? That sounds familiar. Right? Where have we seen something like that before? strcmp. Given this string, does this string come first, or does this string come first, or are they equal, right? That's not technically a comparator, but it's the same pattern, right? A comparator function has the following signature. Right? And I'm going to go ahead and cut and paste this. There we go. So there's some new syntax here. Right? But first of all, before we talk about that syntax, let's talk about the return value. It returns an integer that has the following contract. Right? This is the expectation. Right? It defines the relative ordering. It returns something negative if A is less than B. It returns 0 if A is equal to B, and it returns something positive if A is greater than B, or flip those around. B comes first. Right? Now it's really easy to remember this. Here's how I always remember it. It returns something negative. Where is the think of the number line. We've got negatives, 0, and positives. Right? So reading left to right, it returns something negative if A comes before B, left to right. It returns something positive, right, if they're out of order. And it returns 0, right on in the middle of the number line, if they're equal. Right? So just think left to right, think number line. Negatives, 0, positive, depending on the relative ordering. Okay? Now, the other thing that I would want to emphasize is that it returns something positive, something negative. That you cannot generally read into what the magnitude is. It might be -1, it might be +1. You might have a function that you design so that you can read more information into the absolute value of it or something like that. But in general, unless you put that into your documentation and you enforce that's a little bit of extra information that you want to provide with your implementation, then you can't make that assumption in general. Okay? So that's the return type. CMP, that's just a generic name. Of course, you would name your comparators whatever you're going to name them. Right? but it takes now two items, A and B, and they're const void pointers, right? Both A and B have the const modifier. Right? The comparator will not make changes to them. Will not make changes to them. It only looks at them to determine the relative order, right? So it only looks at them, right? Yeah.
So what if A and B are two different types? Like
That's a good question.
string or B's and int?
That's a good question, and that's on you. You can't have mixed types in C. So the question was, what happens if A and B are different types? Undefined behavior, it doesn't work. Just like if I created a comparator for integers and a comparator for doubles, and you use it for an array of doubles, that's on you. I said that this was a comparator for integers. I put that in the documentation. Why are you using that for the array of doubles, right? That's on you, right? Don't do that. Just like just like absolute value function. There's fabs, there's abs, there's labs. If you end up using abs for a double, well, that's on you. Then you lose precision, right? All right, so there's new syntax here, void star. This is probably our last nothing concept. So we've had the concept of nothing for a while now. Zero, that's the value nothing of nothing. You've got the null terminator character, which is a different kind of nothing. The nothing character. You've got null, which is a special nothing pointer. You've got void. When it's a return type, that means that the function doesn't return anything. In this case, though, the void. This is a generic void pointer. Right? It is a pure memory address that can point to any memory location containing any type. Right? It can point to an integer. It can point to a double. It can point to a string. It can point to whatever. Right? It's been made generic. It's a void pointer. The type has been taken away. It's just a pure memory address. Okay? Why would you want that? Because you want this to apply. You want to pass this to a sorting function, which we're going to do hopefully by the end of the day, and you want it to work on any type. Right? Any type means that you have to take away all the information about the type, but you still need to know how to compare it. If I gave you two integers to this comparator function, it needs to know that they're integers so that it can use less than or equal to. If I gave it two films, then it needs to know that they're films so that it can look up the title and then do a string comparison. Right? So how do we do this? Inside the function, you cast the inputs A and B as the expected types. And like you asked, what happens when somebody passes in something that's not of the expected type? That's on them, right? This is a comparator for films. You can't use it to compare a bunch of integers, right? So I put that in my documentation, and I mean it, right? Don't use it for integers if it's for films. Then you apply the logic for comparing the two elements and return an integer value. Okay? Now let's see this in action over here in the CS50 IDE. I took this away for a good reason here because I want to back this up. There we go. All right, there. And I'll bring this over here. I wanted to avoid spoilers. Okay? All right, so I've got the same array here as I did over in Java. Let's go ahead and make a comparator function for integers because that's what we want to sort here, right? So int CMP for integers, right? And int A, int B. Is that a comparator? Does it follow this signature? It returns an integer, but it does not take two const void stars. That is not a comparator. It is only a comparator if you have that signature, period. Right? It has to have that signature or it's not a comparator. Okay? So step one, convert the inputs to the expected type. Go ahead.
Do you mean it's not like a legit comparator?
Correct. That's why strcmp is not technically a comparator, because it does not take two const void stars. You would have to adapt it or make a wrapper function to make it into a real comparator. Right?
Oh, okay.
All right, so the way that I convert those two is I just need two other variables, right? Const int star x, and I will do an explicit typecast here of a, oops, and const int star y is equal to const int star of b. In other words, I've converted a and b. They're just memory locations, and now it was a pure memory location pointer, and now I'm saying make this into a pointer that points to 4 bytes representing an integer, and that's what I've just done. Now I can treat those as integers, right? Because before, if I just did less than or equal to, then I would be comparing memory locations. So if x is less than y, then I will return something negative. Might as well just go with -1. Now, is this how you compare integer pointers? Nope. This is a pointer. I want the value stored at that pointer, 5 and 10, say. Right? 5 is less than 10, so 5 comes first, and we return -1. Well, how do I do that? Is that correct? Careful, what does that do? That takes a regular variable and turns it into a pointer. I have a pointer, and I need to turn it into a regular variable, so star. All right? So if the value stored in x is less than the value stored in y, then we return -1. Else if the value stored in x is greater than the value stored in y, or you can switch those around if you want to, then I'll return something positive. Again, I could return anything positive, 42, right, 101, whatever you want, but I'm going to go ahead and keep it simple. Just return 1. There's no reason to return negative or 42, right? Unless you were being clever or something, right? Otherwise, the only other case here is that they're equal, and so return 0. There's my comparator. Okay? Now, how do I use that comparator? Right? Once you have a comparator, you can provide it to a standard library sorting function. That standard library sorting function is called Quicksort. Why do you think it's called Quicksort? What do you think the Q stands for?
Quasi-sort?
What was the sorting algorithm called? It was quasi-linear, but it was called Quicksort. And historically, it was originally a Quicksort implementation. But it doesn't have to be. In fact, I've never seen a modern implementation of this that is actually a pure recursive quicksort. Instead, it's some sort of a modified merge sort or tim sort or something like that. Right? So what are those 4 arguments that Quicksort takes? First of all, it doesn't return anything. It's a void function. A void star base is the array you want to sort. Is it an integer array? Is it a double array? Is it an array of strings? Yes, 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 and no, 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 right? It's anything. It's a generic void pointer. We don't have a quicksort for integers. We don't have a quicksort for doubles. We don't have a quicksort for strings. We just have a quicksort that can quicksort anything, right? As long as you give it a comparator to compare things. And we'll get to that here in a second. Nel is the number of elements in the array, right? You've had to do that now this entire semester. You pass an array, you also have to pass the array size, right? The third one here, though, size, is the number of bytes each element takes. Why would I need to know that? Here's an integer, here's an integer. Oh, they're out of order. Quicksort needs to swap them. It needs to know how many bytes to copy over here so that it can copy those many bytes over here and those many bytes over here. For an integer, that's going to be 4 bytes. For a double, that's going to be 8 bytes. For a film, that might be 40 bytes. It needs to know how big that chunk is that it's going to swap with something else, right? And that's why you need to tell it. Now, if it was an array of integers, then you would use size of int. If it was an array of doubles, you'd use size of double, etc. Right? Just like we've used with malloc. Finally, compare is a function pointer that points to a comparator that Quicksort will use. Will use to order elements. That's something new that we'll talk about next week. What is a function pointer? Very high, very quick here. A pointer points to a memory location. That memory location can store an integer. It can store a double. What else is stored in memory? Code. That memory location stores a function, right? And then what you can do is say, give this function to another function so that function can call that function, right? Pretty cool. It's almost meta programming. Let's look and see how it works. So here's Quicksort. I need to pass it the 4 elements. Those 4 elements are the array that you want to sorted, which is array, the size of the array, which I've already put into a variable called n, and the number of elements, the number of bytes that each element takes in the array. Size of int, because we're sorting integers. Now, the last one here is the comparator that you want to use. To pass in a comparator, we pass in the function name, cmp int. We don't use parentheses. Parentheses means you are calling the function and invoking it when you are passing the result of that function. That's wrong. We pass just the name of the function. That's it. Just the name. So cd code, gcc, demo. Let's run it. What would I expect? That thing to be sorted.
Wow.
I didn't have to write a single piece of code myself to actually sort anything. All I needed to do was write this comparator to order stuff. What if I wanted to sort it in descending order now, though? All I need to do is change the comparator. Everything else stays the same. Let's make another comparator. Yeah, go ahead.
So that just tells it how you want, what you want to compare. So like the compare it, that only says like what you want to compare, and like the actual comparison like greater than, less than, blah blah blah.
All that's taken care of inside.
Quicksort does the rest for you.
Exactly. So this is something that we'll go over next week, but here's the visualization of it. The sorting algorithm is generic. It doesn't know what these things are. So we input an array, and any time that it needs to know, are these things in order? It passes those 2 things off to the comparator. The comparator returns something negative, 0, or something positive, depending on the relative ordering. Now the sorting algorithm knows to swap these or leave them alone, right? And so that's how we can do this generically and only have one implementation. One implementation to rule them all.
And then you can use binary search.
We'll look at those implementations too next week, right? For binary search, linear search, etc. In fact, we'll build our own linear search based on this idea. What if I wanted to sort it in descending order? Well, I need a different comparator with a different name. I could copy paste, I could copy paste all this stuff, right? There we go. I could copy paste all this stuff, and the only difference would be greater than and less than are swapped, right? Or I could,
Oh, but that changes the original array, doesn't it?
Oh, it does change the original array, yes. Right? Because, good observation. Why? The original array is not const. It's not because we want to sort it. We want to change it, or Quicksort wants to change it because it's going to rearrange it, right? All right, so how could I write a one-liner here by reusing code? This orders them in ascending order, 1, 2, 3, 4, 5, right? Just like down here. How could I reverse that? Oh, good, or I could go ahead and negate it. Why? Because positives become negatives, negatives become positives, 0 stays the same. But your answer is even better. B, A. Right? Return that value. Swap them and return the opposite value. When I've done that, all I need to do is replace this comparator, everything else stays the same, and, oops. What do you mean it's not there? It's right there.
Oh, you need to put comparison int before comparison int.
Oh, thank you. Duh. There. The ordering mattered there because I was using it. Thank you. And run this. There. 876554321. And I've got just the opposite order here. Right? You don't need to write your own sorting algorithms. You only need to write your own comparators to determine, does it go like this, they're out of order, or they're equal. That's it. Right? Really, really quickly here, how do you do that over here in Java? Right? With Java, you've got, so we'll review this on Tuesday, but you've got a public static comparator function, not a comparator function anymore, but you have a comparator for, say, integers. I'll just call it CMP for now. Here's some new syntax for us. And there we go. I need to bring this in, of course.
It's an A. You're missing an A in comparator.
There we go, thank you. Did I match it over there? Yep. And import that. There we go. And generate that code for me. Thank you. I've got this method called compare that takes one integer. I like to call them A and B, not O1, O2. A and B. And it returns that same logic. If A is less than B, then we will return -1. Else, if A is greater than B, we'll return 1 or 42 or whatever. Otherwise, we'll return 0. There we go. I've got my comparator here. I'll call it a CMP int just to be consistent with what we were doing in C. And now down here, instead of selection sort, for this one, since I've got an array, it's arrays.sort. Not parallel sort, but you can do that one too, I guess. Array and a comparator. What are you complaining about? Okay, there's not a sort method that will take comparator for integers. Fine. What is there a sort for? No, that's not what I want.
Interarray sort Java.
No, it might not allow you to do this. I want to see what sorting algorithm. It doesn't have sorting for. No, there we go.
Sort
It doesn't. There. You're right there. Sort specified array of objects. It's because it doesn't like this. Fine. It wants it to be a big I integer. There. Now it's happy. Right? Because this is what we'll cover next week. This is called parameterization. What is this a comparator for? Just like a list is for integers or a list is for doubles. This is a parameterization. You cannot parameterize based on primitive types. It has to be an integer here. And so consequently, this parameterization has to match this over here. I could get away with a raw type or something like that, but that's not good. Don't do that. Right? In fact, it wouldn't even let me compile there. But here, you can see that it does the same thing as selection sort. But I didn't have to write the code.
But aren't integers immutable? Like big I integers?
Big I integers are just a wrapper of little I integers. The big I integers are the class version of little I integers. Little I integers are just primitives. That's it. You can't use them in collections. You can't create a list of small I int types. L equals new array list. Right? You can't do this. It doesn't allow you to do primitive types like that, but you can do this. Right? And in fact, if you've got an array or a list of integers, you can also go collections.sort. Come on. collections.sort, there we go. List, I'll rename this list. And my integer comparator over here. There we go. Come on, bring that in. There. So arrays.sort if you've got a regular old array, but it needs to be an object array in general. There is another version, by the way, that does not take a comparator. Arrays.sort. And if you just, come on, I don't like its completion there. There. That one does not require a comparator, but that means that it's going to go in the default ascending or natural ordering. Natural ordering for numbers is on the number line. Negatives, 0, and then ascending 1, 2, 3, 4, 5. Same thing for doubles. For strings, the natural ordering is going to be lexicographic ordering, ASCII text. So if you've got a list of strings or an array of strings, you can sort it like this, and it will give you the natural ordering of it. If you want a different ordering, or if you have a different type, like a film that has a title, a director, etc., then you have to use a comparator, because it doesn't know anything what the natural ordering of a film is.
But for this, where it's just a string of integers, or an array of integers, it would work just fine.
Yep, in fact, it would work for both of these. I could, there's the natural ordering right there. Right? All 4 of these are going to do the same thing, ascending order, but that's just because of how I define this. In fact, there's an even better way of doing this. Integer compare to. Yep, this is Java 8. Ooh, new syntax there. That is the method selection operator. Don't worry about it. If we have time, we'll get into it. All right, any questions here or online?
Definitely going to try to use this on the assignment 5.
Oh, where would you want to use this on assignment 5?
I'm thinking the Sudoku one.
Okay, because then if you sort it, you could say, is it equal to Sudoku? If you sort it, you could go 1, 2, 3, is it 1, 2, 3, 4, 5, 6, 7, 8, 9? Or in fact, is this array equal to this canonical array up here of 1, 2, 3, 4, 5, 6, 7, 8, 9?
Yes.
Yeah, excellent.
But I'll need to make a copy of.
You'll need to make a copy that you'll get this row, or you'll get this column, or you'll get this quadrant. Get this row, get this column. That sounds familiar. Assignment 4. So once you've got those into an array, then actually that also sounds familiar. 1, 2, 3, 4, 5, 6, 7, 8, 9 in any order is a permutation.
Except, did we define a permutation as 0 to whatever?
I don't remember if it was 0 to n-1, but you can modify your code, of course.
Yeah.
Okay?
Wow.
All right. Have a good day.